So this is where we had stopped in previous class. So we looked at our residential air conditioning system, which doesn't have a provision for ventilation. Okay, so this was the schematic which we looked at, and I told you that even though the air conditioning apparatus in this schematic looks as if it is outside the room, but it is inside the room. We just have to follow the path of the airflow. So just to enhance our visualization, this apparatus has been kept outside the room. Otherwise, of course, you know that the indoor unit has to be inside the room. So what we discussed was in order to appropriately draw the process line at steady state. So all these calculations which we are doing are at steady state. But you know that in reality, our systems do not operate at steady state, and hence we have done that cold storage experiment in our lab. So we'll assume for the simplicity that everything is at steady state, and at steady state, one needs to know what is the load on the room. And load on the room should be divided into sensible and latent load. Because in any cyclometric process, you not only need to know the enthalpy change, but you also need to know what fraction of that enthalpy change is going into latent and the remaining would be in the sensible part. So that's what will fix the slope of this process line. Okay, so since we have not discussed, and it will take a lot of time to discuss in detail how we can estimate the QS and QL. So these things, let's assume that it would be given to you. So once that is given to you, and let's say the airflow rate is given to you, so then you can estimate the slope of this line, what should be the process line, so on and so forth. Now, what is this I is the indoor condition that you want to maintain. This is again at steady state, so steady condition that you want to maintain. And against that steady state only, this QS and QL has to be evaluated. What it means is if someone is looking at maintaining 16 degrees C inside the room and someone else is looking at maintaining 25 degrees C inside the room. Now the 16 degrees C fellow will actually see larger heat leak from outside, which is let's say at 40 degrees C. So if you just even look at the conduction heat transfer across the wall, Ka dt. So this dt is higher for this fellow. Whereas for the other fellow who is maintaining 25 degrees C, for that fellow, it's only 15 degree, whereas for the previous one, it was 24 degree. So your conduction load or so conduction heat leak from the outside to the indoor would be higher. So whatever you want to maintain as the indoor condition, against that only you should be able to calculate what is QS and QL. Okay, and the major contributor in QS is the heat leak from the wall surfaces. Now during the daytime, it is a combination of conduction, convection, and radiation. Okay, during the night time, it is mainly conduction and convection. Whereas if you look at the latent load, this latent load, major contributor is of course the presence of human beings, and it is very prominent in case of say halls or commercial spaces or office complex where large number of humans are present in a small footprint area. So there you see the QL component, the latent component, is mainly because of the presence of human being. We perspire, we do various activities. Think of a gym where we are carrying out different types of exercise and we perspire a lot. So you will have huge amount of latent load over there. Whereas in a bedroom, especially when we are sleeping or not doing any major activities, there the latent component is not that high. In fact, if you are even walking or watching movie, you would feel that you are comfortable. But once you sleep, you will feel that the room has become too cold for you. It is because of your body's inactivity that leads to lesser QL and hence lesser load on the system. And it seems as if the air conditioning is suddenly cooling too much. So this QS and QL is very, very important. So the second component in the latent load is the leak. You know, if you have doors and open windows, you will have a lot of air coming in, and that will bring in moisture. And none of our, especially in our country, the build quality of our rooms are not very good. So we have lots of gaps in our window frames and door frames. So even though they are closed, there are a lot of leakages. And especially in the older homes, there could be ventilations which were provided. And even if we seal them or try to seal them, there will be leakages. So that also brings in both QS and QL. In fact, human activities is also leading to some amount of QS. We'll see some general trends and numbers, how human activities can lead to sensible as well as latent load. So these things matter. And then, of course, your apparatus dew point, your apparatus conditions will also matter. What is the airflow rate? What is the heat exchanger area? So on and so forth. So once your I is set, once you know what is QS and what is QL, you will have to fix the process line. And if you fix the process line, if you extend it to the saturation point, you will get the room's ADP, okay, or the apparatus dew point required for this room condition. Okay, and that has to be supplied or that has to be met by the air conditioning apparatus, that is the indoor unit, evaporator coil. So at steady state, they will actually match. Otherwise, there is no steady state. And your supply temperature and relative humidity would be given by how much of dehumidification is happening and how much of cooling is happening in the air conditioning apparatus. And you will see that has to match QS and QL. So this is your QS and this is your QL. So this amount of latent heat has to be removed by the air conditioning apparatus, and this amount of sensible heat has to be removed by your air conditioning apparatus. In case you have more number of people inside the room, you will see that this slope will move somewhat like this. And there could be a condition where you are well below your limiting ADP, okay, where you do not get an intersection between your saturated line. So you cannot specify the ADP. So that may be your desired condition, but that cannot be met by your air conditioning apparatus. So that is when you will start feeling uncomfortable. Okay, so at steady state, the room's sensible heat factor has to be met by the coil sensible heat factor, QS upon QS plus QL. And this is the bypass factor for the cooling coil. All these expressions we have already discussed. So that should not be an issue. So the entire process that is happening is I to S and S to I. Now, the biggest question that one part of the industry is trying to answer is, what should be the thermal comfort zone? Okay, now with the advent of AI and all these data analysis, part of it is now being catered by your onboard sensors and onboard controllers, because it starts to learn, okay, so when so you can map your settings to various conditions. So when the outdoor condition is this is how a person is setting the temperature, or during night time, this is what is desired temperature. During daytime, this is what is the desired temperature. So these things can be now logged by your onboard controller and can be used in future control of the apparatus. Okay, so, but before all this computerized control and things like IoT came into picture, hello, yeah, am I audible?
Yes, sir.
Okay, so we actually went about taking surveys, understanding that what is the requirement of various people coming from various cultural background, various demography, and the ideal place for conducting such surveys was America. So Ashray has done a lot of surveys, and they have come up with a range of uh, dry bulb temperature and humidity ratio within which around 70 to 80% people will feel comfortable. Okay, but this may not be true for one single person. So your thermal comfort, your individual comfort zone may lie beyond this Ashray comfort zone. That is quite possible. So, so it's like a scatter of a lot of data point, and this is the region where we are able to satisfy 80% of uh, the uh, the demand by the people. Okay, and as you try to increase your degree of satisfaction, you will have to cover larger and larger area. So this is a broad range within which people from various backgrounds will feel comfortable. And most of the time, you will see in our country, we tend to recommend around 24 to 25 degrees C as the dry bulb temperature, and somewhere in between 50 to 60% relative humidity for this temperature as the ideal zone for comfort. Again, people coming from mountain region may feel that this is too warm and humid. So they may prefer it to be slightly lower, few degrees lower, and as well as humidity to be slightly lower than this. People coming from uh, seashore, like Chennai, or people coming from Kerala may find it too dry also and too cold. So they may prefer 27, 26 as their comfortable region. So if someone wants you to design any AC and do some load calculation analysis, this is a good ballpark figure to start with. In fact, now because of huge amount of energy consumption by these devices, policymakers are even thinking of raising this temperature to around 26 to 27 and removing the settings that we have in our ACs for setting to very low temperatures like 16, 18. So maybe in future we may come with remotes which do not give us the option to set such low temperatures. In fact, when I was in Japan, I remember in my office complex, uh, everything was set automatically. Even if I manually set it to 22 or 24, it would automatically shift back to 27 degree because that was the set point given by the Ministry of Energy over there to be the ideal compromise between thermal comfort and energy consumption. So if you had come for the physical laboratory, we also used to conduct some survey because this semester runs from January to April, so we get at least the weather variation. So from January onwards, we started taking a survey, and by the time it's March or April, we get some other data, and we can get at least the thermal comfort variation with climatic condition. And these are the questions which are against as per the ASHRAI standard. So, so you see it is all subjective. And from this subjective data, we have to come up with some objective numbers. Yeah, so rate your thermal sensation at this moment. So thermal sensation itself is a very subjective term. So someone has given neutral. Now rate your overall thermal comfort sensation at this point. So you are comfortable. Then what is the thermal environment? Is it highly acceptable, just acceptable? Okay, so then what is the air movement? Is it acceptable to you or not? What is your level of sweating? Okay, so all these questions are asked. What kind of clothes you are wearing, and do you want any change in air movement? So this comfort region is also very sensitive to air speeds. So this comfort region has been given for a particular range of airspeed. If you increase or decrease the airspeed, this region will also shift right or left or up and down. This is a table which gives some average values of heat released by our body while certain activities are being carried out. So you see, while sleeping, we release around, on an average, 70 watts of heat, out of which 75% is sensible. So only 25% of it is latent. When we are seated, quiet, okay. And then if you go to the other extreme, let's say while you are working in an industrial environment, you are releasing 300 to 600 watts of energy. Okay, if you are carrying out exercise, working in a gym, it could even touch 1000 watts or even more, depending on the amount of activities you are carrying out. And you see, as the load or as the heat released by our body increases based on our physical activity, you see that there is also a drastic shift in the sensible heat factor. So when we release a lot of heat, we do not release that heat in form of sensible heat. It's physically impossible because our body has to go very high to a very high temperature to release the heat in form of sensible heat. So what we do is we perspire, and hence you see when our activity increases, almost 65–70% of the heat released by our body becomes in the latent region. So that's why our gyms and all, they are, if you enter initially, you will feel very cold. They are designed for your extreme physical activities. So unfortunately, we do not have a lot of time to discuss and evaluate how to estimate QS and QL. So we'll drop that part. So given that QS and QL is known, we should be able to do some primary calculations for an air conditioning system. So that is the motto of today's class. And you at least know that what contributes to QS and what contributes to QL. So let's now move on to the central air conditioning system, where the air conditioning system can provide you active ventilation. Okay, in our residential space, we can rely on the infiltration of air from outside to inside via gaps in your doors and windows. But when it comes to, say, a large hall or a classroom, the amount of infiltration, which is passive in nature, you cannot guarantee that you will always have a certain amount of infiltration. So that passive ventilation will not work. Even in your bedroom, when you have 10–12 people with your AC on and everything is closed, you will start feeling suffocated. So you'll turn off your AC, open the doors and windows for some time. Again, you will feel thermally uncomfortable. Then again, you'll close the door and start the AC. That is typically what we do in our home when we have too many people inside a smaller area. So in such situations, you need a system which can provide you ventilation, which doesn't make you feel uncomfortable, or lack of oxygen is what we feel as sickness. Okay, in fact, if your central ACs are not providing you sufficient amount of ventilation, you can quickly tell, because you will start feeling sick after some time. It clearly means that your AC is not providing the requisite ventilation. So the system is not a lot different from what we have in our residential ACs. It is just that you have a provision for exhausting some portion of the air coming from the room and taking in fresh air. So if this is your room, you want to maintain it at certain condition I. So I is this state point. Okay, and this is your air conditioning apparatus. It is written as cooling and humidification because we are looking at only summer air conditioning system. So this is your evaporator coil of the refrigeration system. So this is supplying air at a state S. Okay, so as far as the process which is happening inside the room is, it is still the same. Okay, S to I. So that does not vary from what we have in our residential ACs. So S to I is still the process which is happening in your room. Supply air coming in, getting heated up and getting or picking up moisture and leaving at the state I. Now, what is different is what happens outside. So this is your return air, or sometimes also called as exhaust air. Okay, so and this is your supply. So in your classrooms also, when you visit next time your Nalanda classroom, you can see that there are two ductings provided. One actually brings in cold and dehumidified air, and the other ducting is for the return line. Same if you visit any mall, any commercial space, you can check that there are two sets of ducting always provided. Okay, so just because there is a duct doesn't mean that it will supply cold air. So we require two sets of ducting. So ducting is not shown completely over here. So this is the return air. Through a valve, we exhaust some of the air to the outdoor, and the rest is recirculated. Okay, so this is like a valve. We will see how this valve looks like. This is nothing just but a flap. You would have seen in your AC coaches, railway coaches. So it's very similar to that. Or your in your flights also, the uh, there's a knob which you can rotate, or in your car also there are flaps, so you can open and close those flaps. So something of that sort is provided. So some portion of the air is exhausted and the rest is recirculated. And then over here, we have to draw in the same amount of air flow rate which has been exhausted to the outside, so that you still have the mass balanced. So whatever mass is exiting this room is being supplied by the air conditioning system. Okay, so these two gets mixed, and then it passes through this cooling and humidification coil, and then it is again supplied back into the room. Okay, so it is like an active infiltration. So you are actively drawing air from outside. And the reason for this is only one, that is fresh air. You require oxygen to survive. So on a psychrometry chart, this would be the process outside the room. So inside the room, S to I is the same as what we have discussed in the previous slide. Now what is happening in the outside is this mixing is happening. So I, so this is still at condition I, assuming that all the ducts are perfectly insulated and no leaks in the duct. And this is the outdoor condition. So this I and O is getting mixed ahead of your cooling coil in certain ratio to give this state 1. This is the state 1. And now your cooling coil is not seeing I, which was the case in your residential AC. It is actually seeing a load equivalent to 1, state 1. Okay, and now from state 1, it has to supply the air at this state S. So 2 and S is same, assuming that the fan work is negligible. Okay, 2 and S would be slightly different because you will have, if you draw control volume across this, you will be able to write the first law expression for this, H2 coming in, HS going out, and some work input to this fan. So we are neglecting that work input. Okay, otherwise 2 and S would have a slight variation in the state. So it has to supply at S for the condition not at I but at 1. So now in this case, your room sensible heat factor is Qs upon Qs plus QL, but your coil sensible heat factor, and in certain books it is also written as grand sensible heat factor. So it's a grand total. So grand total is coming because you are mixing outdoor and indoor air. So it sees a larger load. Your cooling and dehumidification coil is now seeing a larger load. Okay, and if you exhaust all the return air to the outside and always take fresh air from outside, then you will see the largest load that would be like this. Okay. So as you increase the outdoor air fraction, this 0.1 shifts towards O. So this is your coil sensible heat factor. And also your coil is now seeing a total enthalpy change of 1 to S and not I to S. Okay, so that's why your central ACs, especially if you look at commercial spaces, many a times they will not run it at the optimum ventilation level. They'll tend to reduce the amount of ventilation in order to save energy. Many a times when you visit a mall or a theater, you will have that weird smell inside. So that is the first indication that the ventilation is either completely turned off, so entire air is being recirculated, or it is at a very low setting. I'll come to this example problem a bit later. So this is a nice sketch I took from a website. So how the rooftop units work. So invariably you will see that these uh, central ACs are mounted on the rooftop of the commercial buildings. Okay, so there are a lot of ductings over here. So wherever you see this flap, this looks like a flap. Okay, there is a small motor provided over here which can rotate, or in fact, which can slide this rod, and hence it will rotate this flap. So this is actually called an air damper, and it is used to control the airflow rates. Okay, it is effectively like a valve. So you can open and close a valve. So similarly, you can open and close this flap to increase or decrease the airflow rates. Okay, so over here you see your compressor is there, a fan is there, okay, and some coil is provided. So this is your evaporator coil. This is your condenser coil. Okay, and the compressor is there. Definitely there is a throttling valve, which is not shown in this sketch. So this is your entire refrigeration system. Evaporator coil, compressor, condensing coil, and the throttle valve, which is not seen. In order to cool this condenser, you have these fans. Okay, this is isolated from the cold side. Something similar is also present in your window ACs. So you have two fans in your window ACs. One is for the outdoor unit, one is for the indoor unit. But since everything is mounted in one single box, so there is an insulation which is provided. Okay, you have one fan over here, one fan on the back side. Compressor is placed somewhere in the middle. Air is drawn here. You have your evaporator coil on this side, and then exits through a small opening over here. And you will see a big mesh over here in your window ACs. So this is for suction. It passes through the evaporator coil and it is blown back. Okay, you have the condenser coil on the back side, which is kept hanging outside for a window AC. So this configuration is quite similar to that only. So you have your evaporator coil here, your condensing coil here. This big blower is for the evaporator side only, because it has to blow air all the way through the ducts to your room. This is significantly more powerful. Whereas this fan is less powerful. It is just to draw in outdoor air, pass it through the condenser, cool the condenser and blow out. So our focus, so when we had drawn all the cyclometry processes, our focus is only on this side. We are not dealing with what is happening on the condenser side. The condenser side, as it is just sensible heat transfer. So what you have over here is, again, there is a partition you see over here. Okay, so this partition is to partition the fresh air and the exhaust air. So this is the return air line. Okay, this return air gets bifurcated into two parts. One is outside, the other one is inside. So there is a small exhaust fan to draw air out. Okay, and how much it will, how much of this return air will be exhausted out would be governed by this damper which is provided over. So this and this. So if you close this damper, nothing would be drawn back or recirculated. Everything will go through this. Okay, or if you, the other case is if you completely open this and close this side, then nothing would be exhausted. Everything will be drawn by this blower. The top portion is where we are taking in fresh air. Okay, so you see it is connected to one single damper because if you close the exhaust, you don't need fresh air. If you open the exhaust, you need more fresh air. So the regulation is very similar for both the fresh air and the exhaust air. Hence, we can provide one single damper. So whatever the opening is for the exhaust air can be provided to the fresh air. Okay, so this fresh air comes in, it mixes with whatever recirculated air is there. Okay, and then it passes through this cooling and dehumidification coil. Here it is written heating and cooling coil because this single system can be used now for winter also. So we can use our refrigeration system as a heat pump. So all you need to do is make the evaporator as the condenser and the condenser as the evaporator during winter. Okay, so that's why it is written heating and cooling coil. But for summer air conditioning, this will just be your cooling coil. So this and this mixes, and then it is drawn in by this blower and then supplied to your supply duct. So this is your supply duct and this is your return duct, return supply. Okay, so everything is very compact in one single module. Okay, so this is how your ducting. So you will see your ducting takes a lot of space. Your refrigeration system doesn't take a lot of space. So this is how your rooftop unit can look like. These are some actual photographs. Now our Nalanda system is slightly different in the sense that the refrigeration system is not on your rooftop. It is separately present so that the roof doesn't have to take a lot of load. Okay, so this kind of a system is good enough for a few hundred tons of load, but when it comes to close to 1,000 tons, then it is so then you can have a separate configuration where you do not have to make your roof very strong because you have to withstand all the vibrational loads from the compressor, the weight, the static weight and everything. So you can remove that cost from your construction. You can keep your refrigeration system if you have space on the ground level. Okay, and then supply cold water. So your cooling coil becomes just a cold water supply line. Now this cold water is provided by your refrigeration system. That is exactly what is present in our Nalanda. So the refrigeration system is separately placed on the other side of the road. It is on the back side. Okay, and it supplies cold water to the rooftop unit. Now the rooftop unit has to take only the load of the ducting and the dampers and filters and all, so which is pretty light. Instead of taking the entire weight, static weight of the refrigeration system as well as vibrational load. So the roof need not be very strong if you have your refrigeration system outside. Now, what is the typical ventilation requirement? So again, some numbers are given. The actual figure can vary based on the application and the number of people you expect inside the room. Okay, so these are some recommended numbers. So the unit is air changes per hour. Okay, air changes per hour. So what this unit is, if you have a room of, let's say, 10 feet by 10 feet is the floor area. And let's say, again, 10 feet is the height. So you have 1000 CFT as the room volume. Now, if the recommended value is 1 ACH, it means that it has to change it has to exchange air equivalent to the volume of your room. 1 ACH means the device has to exchange volume of air equivalent to 1 times the volume of your room in 1 hour. So if it is 10 SEH, it means that the device has to now exchange 10 times the volume of your room, that much volume in 1 hour. So it gives you then, so let's say if your room is 1000 CFT volume, and let's say you require 10 SEH as the ventilation. So you require 10,000 cubic feet of air per hour. So this gives you the volume flow rate. Only thing is the units are in a different, provided in a different manner. Okay, so just so that the values are scalable. So this unit has been created so that the values are scalable. So if you have a smaller room, invariably you will require lesser amount of ventilation, assuming that you are not, you do not want to suffocate many people by making them forcefully stay inside that small room. Whereas if you have a large hall, definitely you will require more air ventilation. Okay, but it could be that you have 2 people inside a small room and you have 200 people in a big hall. Okay, and the amount of ventilation required for 1 person is more or less same. It doesn't matter if you are inside a room, small room or a big room. So things could be scalable. If you have 1000 times more volume, you require 1000 times more volumetric flow rate for ventilation. Okay, in case you have no idea in which category you lie, one thumb rule is you assume the ventilation recommended is minimum 7.5 liters per second per person. So if you have 10 people, you have 75 liters per second of fresh air entry, which is the recommended value by ASHRAE. And then for your given volume, you can back calculate what is the ACH. Any doubts over here? So you see over here in kitchen, in restaurants, a huge amount of ACH is required. Okay, similarly in classrooms also there's a huge variation depending on the size of the classroom. So this range is created based on the human density inside the room. So as I told you, if you are not able to evaluate in which category you lie, it is easier to create your own ACH value by assuming 7.5 liters per second per person as the minimum ventilation requirement. And then you see how many people are there inside your one room, what is the volume of that room, and then you can back calculate what is the ACH required for your particular room. Okay, so this was as far as the central AC goes. But if you are looking at how much of infiltration will happen inside your room, so this is passive ventilation. Infiltration is undesirable because it brings in hot and humid air from outside, but at least one part of it is desirable because it brings in fresh air also. Okay, and in order to estimate what is the infiltration, there are various correlations available. So this is one such correlation. Again, the units are in ACH, and people have carried out uh, leakages or leak testing of a particular room. We do not carry out over here, but again, these experiments have been carried out in western part of our globe, and they have come up with certain numbers. So typically, your new house will fall under this tight category, and as the house becomes older and older, it will automatically shift to this loose category. So you will have more air infiltration. Okay, and these tests are actually conducted by closing the doors and windows and then putting a big blower in one of the door or window and trying to pressurize the room. Okay, and then measure what is the flow that you have to provide into the room to maintain a steady state. So at steady state, you will have blower your room. If this is a room, if you're supplying air through a big blower. So at steady state, the air drawn in by this blower would leak out from the gaps in the doors and windows. So it is characterized on the basis of velocities and temperature differences. So whatever your blower velocity is, that is V over here. Okay. And then in natural condition, if you have to predict what is the infiltration, V over here would be the wind speed. Why this T0 minus Ti is coming? Why this factor is also coming? Can anyone tell? In infiltration. T outdoor minus T indoor. What has temperature to do with infiltration? Anybody? You have studied in your heat transfer, no? Natural convection. So this part is forced convection. The other part is natural convection. If you have large temperature difference between indoor and outdoor, that will also create a density difference between air in the outdoor and indoor, and that can create a circulation loop. If this is your room, let's say this is a window and very simple, this is a door. So let's say inside temperature is 20 degree, outside temperature is 40 degree. So what will happen?
Flow of air from inside to outside.
No, it will be equal amount of air would be drawn in and drawn out, but how will that happen? It's not that as if your room is getting pressurized or depressurized. Some portion you will have infiltration and equal amount of exfiltration will also happen. If you move across an air conditioned room from the bottom gap of your door, you can feel that draft, no? You can feel the draft of air coming out. Isn't it?
Yes.
So that is what will happen. Your cooler air will settle at the bottom and will come out, and your hotter air, it will tend to enter through the top portion of your doors and windows. Okay, so infiltration will happen from the top leakages, top surfaces. It will get cooler and it will become denser and fall down, and it will come out from the bottom leakages. So whenever we read this term infiltration, you should also think that there is equal amount of exfiltration. Otherwise, you will not have mass balance. Something will become depressurized and something will become pressurized. That doesn't happen. So if air is coming in through some gaps, it will also leave through some other gaps. So now let's go back to the example problem. Okay. So in an air-conditioned classroom, the cooling load is given as 100 kilowatt with a sensible heat factor of 0.7. So what does that mean? Cooling load is 100 kilowatt, sensible heat factor is 0.7. So what does that mean? So out of this 100 kilowatt, 70 kilowatt is in sensible column and rest would go into the latent column. Okay, and the room has to be maintained at 25 degrees C, 50% RH. That is your comfort zone, your indoor room condition, that is I, which is fixed. So you want to maintain 25 degree, 50% RH inside the classroom. The outdoor condition is given. Okay, 50% of the air is taken from the outdoor condition for ventilation. Air from the cooling coil is supplied to the classroom at a temperature of 12 degrees C. So your supply side dBT is given. Okay, your outdoor condition is given. Your indoor condition to be maintained has been given. The load is also given. QS and QL, everything is given. So what is the sensible and latent cooling capacities of the coil? Will it be 70 and 30? Will it be 70 and 30? So it would have been 70 and 30 straightforward if there was no ventilation. Okay, because there is ventilation and 50% of the outdoor air is mixed with the indoor air. So huge amount of ventilation is there. So the cooling capacity experienced by the coil would be significantly higher than the 100 kilowatt which is present inside the room. So first thing is always mark all the state points in your psychrometry chart. So I is given. Okay, then your O is also given. O is given in a different manner, 42 degree WBT and 28 degree, sorry, 42 degree DBT and 28 degree WBT. You have to mark these two lines and the intersection point is your state point O. Okay, and then it is given that 50% 50% is the requirement for ventilation. So 50% outdoor and 50% indoor. So it is very simple. You mark the midpoint of I and O. So that would be the air which enters the cooling coil. So that is your state point 1, which we marked in our previous slide. Right. So this state point 1. Point 1 is mixing of I and O. Okay. Now on your supply side, only one information is given, 12 degrees C. So how do we get the state point S? With one information, we cannot pinpoint. So all we can do is we draw a vertical line. But how to get this point? We can only draw a vertical line of dBT equals to 12 degrees C, because that is the information provided. How do we mark this point? So we make use of the process happening inside the room. So process happening inside the room is 3:7 latent is to sensible. So this is the ratio of latent heat to sensible heat. Okay. Now this ratio will be equals to latent enthalpy change by sensible enthalpy change. Okay, and some information is provided at the bottom of the question regarding the latent enthalpy change and sensible enthalpy change in terms of HFG and CPM. CPM is CP of moist air, very close to 1 only. So if I make use of this fact, then I can actually obtain the humidity ratio. Because this point I is fixed. All we need to now fix is the state point S. Okay, 1 is also fixed because I and O, you draw the line, you bisect it, 50 is to 50, 50, 50, no? Bisect it, you will get the state of 1. That is after mixing of outdoor and indoor air. So this is the entry to the coil. But the exit from the coil, that is supply condition, is not yet fixed because all we know is the temperature. So we have to fix the humidity ratio or WBT or relative humidity. Something has to be known. So we can fix the humidity ratio by using this expression. So 3:7 is the ratio of HL by H sensible, and the H latent part is omega S minus omega I times HFG. So whatever the enthalpy, whatever the humidity ratio is over here, minus the humidity ratio of this. Okay, this difference times HFG is your latent component, and the temperature difference between I and S, that is given 18 degree, or no, sorry, 25 minus 12, so 13 degree, times the CPM would be your sensible enthalpy difference. So over here, you know this, know this, know this. You just get this omega S. So once you get the omega S, plot it over here. Wherever it intersects the 12 degree vertical line, that fixes your supply side condition. Now, once everything is fixed, you finish off your entire process diagram. Okay, air from the indoor condition gets mixed with the outdoor, comes at this state point 1, enters your cooling and humidification coil, leaves at this state S, and again enters the room at I. Oh, sorry, after mixing with the room, it becomes I. Okay. Now, once everything is fixed, now you can obtain what is the cooling load on the coil. The cooling load on the coil would be the enthalpy difference over here times the mass flow rate of air. Okay, so this is per kg of dry air. So you have to multiply it with the mass flow rate of air. Whereas what is given over here is in the question is this is the total load in the room. This is the total load in the room. This is the total load felt by the coil because of the additional enthalpy brought in by the outdoor air. Now this is 100 kilowatt. You can find out how much is this. Okay, what is the coil ADP and bypass factor? Again, straightforward. Once you mark the S, you know 1, extend it till your saturation line. That will give you your ADP, apparatus dew point. From there, you can find the bypass factor. Mass flow rate of air, again, straightforward. You now know that the room load is 100 kilowatt. You know the state point S, you know the state point I. Okay, so this enthalpy difference times mass flow rate of dry air equals to 100 kilowatt. So from there you can get the mass flow rate of dry air, and you can multiply it with the other larger enthalpy to get the total enthalpy change across the cooling coil. Either way you can do it. Either you can straight away use this unitary method. This is 100 kilowatt. How much is this? Or you actually find out what is the mass flow rate of dry air through the supply or through the room, and that is the same mass flow rate of dry air through the cooling coil, and you can multiply that with this enthalpy difference. You'll get the same answer. Volume flow rate of moist air over the coil. To answer this, you'll have to look at the density lines. Okay, so you see these are the density lines. Okay, so you'll have to do some interpolation. So what would be this density? Well, actually, these are specific volume lines. So 1 over this will give you the density. The amount of water condensing on the cooling coil, again, it is once you have all the state points, all these parts can be answered. So once you have this, so how much of water will be condensing on the cooling coil is this much. Not the room condition, because cooling coil is seeing a mixture of indoor and outdoor air. So it will have to dehumidify a huge amount of air. So the latent load on the coil is huge. Best is, I would suggest you not to use ES for this part of the problem, because air conditioning problems are much faster to solve using the cyclometric chart. And then what is the power consumption by the compressor if COP is 4? So you know the answer to the first part of the question. So that is Q cooling coil is whatever it comes. Let's say 200 kilowatt. Let's say. So then your power consumption would be 50 kilowatt for 4S COP. 4S COP is very good. Okay. Any doubts? Any doubts in how to mark the state points? See, over here, the enthalpies were not known explicitly, and hence we had to use that expression of enthalpy change in the latent part and enthalpy change in the sensible part to obtain the humidity ratio. Okay, without this, it is not possible to mark the state point S. No doubts, no questions. Okay, so this is all from the air conditioning part. So this is the end of your syllabus then. So anything you want me to discuss, any doubts you have? Nothing. So you want me to discuss the tutorial?
Yes, sir.
Okay. So this last tutorial is combination of compressor, expansion device, and air conditioning processes. Let's see what questions. Okay. I think last question is very similar to the example problem. Sixth question is on compressor as well as capillary tube. Fifth question on capillary. Okay. So these MCQ problems, first question, the refrigeration capacity of a reciprocating compressor increases as actually the statement is wrong. The refrigeration capacity of a system using reciprocating compressor increases as the evaporator temperature decreases and condensing temperature increases. As the evaporator temperature increases and condensing temperature decreases. As the evaporator and condenser temperature increase, as the evaporator and condensing temperature decrease. So which one do you think? So you have a refrigeration system using reciprocating compressor. Which combination will lead to increase in refrigeration capacity? We've discussed so much on refrigeration capacity. We've discussed so much on cycles. Okay, so this is your T evaporator, this is your T condenser. In which condition? So you please look at what are the options. Which condition do you think your refrigeration capacity? So your refrigeration capacity is a product of refrigeration effect. This is your refrigeration effect. Refrigeration effect is nothing but the difference in the specific enthalpies at the exit and inlet of the evaporator. Okay. Times your mass flow rate provided by the compressor. This product is your refrigeration capacity. Now you check which combination will lead to increase. Let's close this. Increase in RC.
Evaporator temperature increases and the compressor temperature decreases.
Yes. So you will see that as you bring the two temperatures closer to each other, your RE increases and your m dot will also increase. I think these things have been discussed in class also. So as you bring this temperature lower and push this temperature up, bring this temperature lower, you will see that now you will have this much as your RE, whereas earlier you had only this much. So your refrigeration effect has increased. Okay, the pressure ratio, PC over PE, that is a pressure ratio across your compressor has reduced, which leads to increase in volumetric efficiency. And hence mass flow rate will increase. Additionally, since your suction pressure has increased, your rho E has also increased, which again leads to m dot refrigeration increases. So there are multiple effects which are coming into picture. RE has increased, m dot has increased because of additional volumetric efficiency. M dot has increased because your suction is happening at a higher pressure and hence your densities at the suction are higher. So answer is B. Yes. During every pull down period, the reciprocating compressor is likely to be overloaded because the initial refrigerant mass flow rate is high and specific work of compression is low. The initial refrigerant mass flow rate is low and specific work of compression is high. Both of them is high in the initial period and none of the above. Which one is correct?
A.
Yes, A. So initially, when both evaporator and condensing temperatures are equal, the specific work of compression is going to be negligible. In fact, it is zero if you look at thermodynamics, but you'll still have some frictional losses in your compressor and also it'll have to overcome that. So theoretically, it becomes zero, but the mass flow rate drawn in by the compressor is very high. And that's why the product of that gave us that parabolic nature curve. Consider a process in which moist air at 40 degrees, 60% RH passes over a cooling coil and comes out at 25 degrees C. The mass flow rate of air, dry air basis is 1000 kg per hour. The refrigeration capacity of the cooling coil for this process is measured to be 1.5 Artan. Is the process possible? If yes, then what is the value of RH at the exit of coil? If no, then why the process is not possible? So how do we approach this problem? First, mark the state point, 40 degree, 60% RH. Has anyone done this problem?
Yes, sir.
So you know the mass flow rate of dry air, you know the cooling capacity. So from there, you know the enthalpy difference, isn't it? So This is your 40 degrees C and 60% RH. And you know the M A dot, and you also know QC. So from this two information, you know what is the enthalpy difference or specific enthalpy difference. This is your isenthalpic lines. Okay, now process could be anything. And then you'll have to mark the 25 degree dBT on this. So are you able to get an intersection? Okay, let's see, then I'll have to solve the problem completely now. Can anyone tell me at least quickly what is the enthalpy, specific enthalpy difference between the
42 I got it. 42 kilojoule per kg.
42 kilojoule per kg? Okay.
Sorry, if you can confirm with.
Let's get a clean information. Let's use the ES then. You have used ES or just from the psychrometric chart you are doing the problem?
So from the chart.
So your QC is 1000 kg per hour. And your refrigeration, sorry, not this is QC is 1.5 atom. So delta H will be C over MA. With 19. Cooling capacity is 1.5 R ton. 1000 kg per hour is the flow rate. So QC equals to MA times delta H. So if I divide QC by MA, I should be able to get the delta H value, and it gives 19. Is anyone getting this 19? Then we can plot it over here. So we'll look at 40 degree and 60% RH. Okay, difficult to plot here. Can we get an intersection? Now this is 60%. Yeah. So this is the state point, and you will have to read the enthalpy. So up to 100 you can read here. From 110 onwards you read here. So this will be probably somewhere here. 115. And from there you subtract 19. So 106, 96. 96. This is your isenthalpic line, and this is your 25 degree line. You will not get an intersection. No? You will not get an intersection. Were you getting an intersection? Because with 42,
No,
I
sir.
think you. Exactly. So in order to cool to 25, you will have to expend this much amount of energy. So with 1.5 R ton, you will not get 25 degree C as the outlet air. Yeah, I think this is clear. So once you make the state points, you will be able to decipher if this process is possible or not possible. Okay, if the outlet air is at 90% RH, if yes, then what is the outlet temperature? If no, then why is the process not possible? So now in the next problem, we are stating that the outlet enthalpy, outlet relative humidity is 90%. So the parameter has now been changed. So this was 40 and 60, yes. And then again 96, you have to mark. And wherever it intersects 90%, that is your condition. So this is your 40 degree, 60% RH. Exit condition is given as 90% RH. And you know the enthalpy difference is 19 kilojoules per kg. So this is your answer enthalpic line, wherever it intersects. So this is going to be your process. This process is possible. Clear? Clear or any doubt? Somewhere I have gone wrong. If you feel, you can tell me your solution.
Sir, no, sir, no doubts.
No. Okay. A standard capillary tube of 1.21 millimeter diameter, 1.5 meter length is chosen for operating at condensing temperature of 40 degrees C with something is missing with R134A as refrigerant. The refrigerant is saturated liquid at the inlet to the expansion device. Basically, it is saturated liquid at the exit of the condenser. So the standard rating chart for this capillary tube is provided. The desired mass flow rate through the compressor is 6 grams per second. Will the standard capillary tube of this dia and length be able to provide the desired mass flow rate? If not, then determine the length and diameter of the capillary tube which can deliver the desired flow rate. So it is just looking into the chart. So use the following chart. The formula is M actual equals to MR into phi. MR is the reference flow rate for the standard capillary tube. Okay, so the standard capillary tube dimension is 1.21 mm dia and 1.5 meter length. And for all other diameters and lengths, you will have to use a correction factor, which is phi. Okay, so this is the correction factor, and this is the mass flow rate through your reference capillary tube. So your actual will be reference times the correction factor. And now even in your actual, the mass flow rate is given as a function of condensing temperature. And even at one condensing temperature, if you have different amount of degree of subcooling from your condenser, then also your mass flow rates are varying. If you have saturated condition, this is the purple line is the mass flow rate line. If you have more amount of subcooling, your mass flow rate through the capillary tube increases. Okay, so this is that plot, and this plot is drawn for a standard capillary tube. And this is the correction factor for other diameters and lengths. So all we need to do is check if at 40 degrees C and saturated condition. So 40 degrees C saturated condition. 40 degrees C saturated condition. The mass flow rate is around 16 kg per hour. So is it equal to 6 grams per second? Let's look at the calculator. 16 kg per hour, so 16,000 grams. So no, so it cannot deliver. It can only deliver 4.44 grams per second. So now you will have to size the capillary tube. What should be the diameter and length? What we require is 6 times 21,600. 21.6 kg per hour. 21.6 kg per hour, and this delivers 16. So what is the correction factor? 1.35. So look for the 1.35 line. This is somewhere here. This is 1.5. Let's just draw a line somewhere there. So wherever it intersects. So 1.46 as the diameter, and length is somewhere between 2,500 to 3,000. Maybe close to 2,500. That's it. So you require a capillary tube of 1.46 mm dia and 2.5 meter length. That's the answer to the second part. Questions? So this is eventually how we size it in the field. In the field, we'll not run the ES code which I have shown. Okay, what ES gives you is this. So ES will be able to give you this. So at various operating conditions, you can predict, or for a given mass flow rate and inlet condition, you can predict what is the length and diameter required. So what ES gives you is this entire chart. And now you use this chart in the field to back calculate the diameter and length. So what I had shown in the class was how to get these values. And what I did in the class was just one data point. So inlet condition was, I think, 40, 45 saturated, and some mass flow rate I had chosen for a particular refrigerant. And so it's basically one point on this entire chart. So one can create this entire plot by running the ES code. Questions, doubts in this problem? I think this was straightforward. Just reading the chart. Okay, next problem is R134A is used for domestic refrigerator with single cylinder hermetically sealed compressor having 5 cc displacement volume operating at 30,000 RPM. The design evaporator temperature is minus 20 degrees C, condensing temperature is 50 degrees C, assume 3% clearance ratio, polytropic compression, V expansion with n equals to 1.1. Everything is given. Basically, you have to find out the volumetric efficiency from all this information. The refrigerant state at the exit of the evaporator is saturated vapor. However, it enters the compression chamber with 20 degrees C superheat. Okay. So this is where only you have to be careful. So when we discussed about the mass flow rate for drawn in by the compressor, so we always have that rho sitting over there. So rho at the suction condition. And in our classroom discussion, we had assumed that the suction to the compressor is exactly the same state as exit from the evaporator, but it need not be. Because of poor insulation, you can have an LSHX. Okay, so there could be other reasons like if hermetically sealed compressor, so you have to do the motor cooling by the refrigerant itself. There is no external media to cool the motor. So in order to cool the motor itself, the refrigerant, by the time it enters the compressor, could be superheated. So due to multiple reasons, there could be a change in state of the refrigerant between the exit of the evaporator and entry to the compressor. So entry to the compression chamber actually. So that is given over here as 20 degrees. So when you're using the density, you have to use the density at this inlet condition to your compressor and not the exit from the evaporator. So, and it is given that refrigerant superheat is useless as it picks up the heat from crankcase and motor windings. Now determine the following. What is the volumetric efficiency of this compressor? For volumetric efficiency, you check the formula. You have all the information over here. The pressure ratio, for pressure ratio, you have to check what is the saturation pressure at -20, saturation pressure at +50. Take the ratio, N is given, clearance ratio is given. So from all this, you should be able to get the volumetric efficiency. What is the mass flow rate delivered by this compressor and what is the refrigeration capacity? Mass flow rate delivered would be rho times volumetric efficiency times displacement volume. Okay, and rho has to be calculated at whatever the saturation pressure is at -20 and the temperature is +20. Okay, that is the only thing you have to be careful. Refrigeration capacity, you complete the cycle, thermodynamic cycle, get the enthalpy values. Remember, the exit from the evaporator is saturated vapor. So you should not count this -20 to +20 rise as useful refrigeration effect. It is useless. Now if
Sir,
this yeah.
Sir, the compression chamber enters at 20 degrees superheat, means the temperature is 0 degree, right?
Yeah, it is 0 degree. Sorry, my bad. So temperature is 0 degree. So this entire 20 degree superheat is useless. Okay, so it will not go into the refrigeration capacity. If this compressor is coupled with a capillary tube having mass flow rate characteristic as shown in the plot below, determine the steady state evaporator temperature. Okay, so now in the previous problem everything was given. Now it is a reverse calculation. So you have to find out the balanced evaporator temperature. If you couple this compressor, whatever the specification is given over here, to a capillary tube having this as the characteristic flow rate. Okay, so now this becomes a hit and trial problem. Assume that the evaporator temperature is -20. Get the mass flow rate through the compressor. Check at -20. At -20, what is the mass flow rate delivered by this capillary tube? If they do not match, you check what is the difference. Okay, and based on that, you will have to make the next guess. It's a tedious problem in that sense. Okay, so first guess is whatever the evaporator temperature is given, you assume that -20, you know what is the mass flow rate drawn in by the compressor. Check if it can be delivered by this capillary tube at -20. If it is able to deliver, then this is your balanced condition. Okay. If the mass flow rate drawn in by the compressor is more at this condition than your capillary tube, then obviously your next guess should be a lower evaporator temperature, isn't it? Because a lower evaporator temperature will further lower the mass flow rate through the compressor. So you have to reduce the mass flow rate drawn in by the compressor. If the mass flow rate drawn in by the compressor is less than what the capillary tube can deliver at -20, then your next assumption should be a higher evaporator temperature, because higher evaporator temperature will increase the mass flow rate drawn by the compressor. So based on which side you lie of the with respect to this plot, you have to make the next guess. Okay, consider the scenario where the compressor speed is reduced to 1000 rpm with condensing temperature at 50 degrees C. What will happen to the new steady state evaporator temperature? Will it increase or decrease? Explain via plots. So let's assume that you get an intersection at, let's say, 5 degrees C in the question number C. Let's say this is your intersection point where your mass flow rate through the capillary tube, which is choked in this case. That's why you do not see any change in mass flow rate. Effectively, this capillary tube gets choked at 10 degrees C. Anyway, so let's say this is where you get the balance between the compressor and the capillary tube. Now the next problem is, now instead of operating your compressor at 3000 RPM, you are operating at 1000 RPM. What will happen to the mass flow rate through the compressor? What will happen to the mass flow rate drawn by the compressor? Come on, guys. For this you need not think so much. Instead of 3000 RPM, if you are running your compressor at 1000 RPM, mass flow rate will reduce. And your next balanced condition will happen at a much reduced refrigerant mass flow rate, which means that your evaporator temperature will increase. Otherwise, you will not get a balanced condition. So your next steady state evaporator temperature will be much higher. Not clear. I'm not getting any response from you guys. It's not clear. Hmm? Not clear from the explanation. So this is your capillary tube. This is the evaporator. Let's say your balanced condition is this, when your compressor is operating at 3000 RPM. Okay, but when your compressor is operating at 1000 RPM, your mass flow rate would reduce tremendously. So it will be 1/3 basically. So your compressor can only provide this. Or rather, sorry, this is your capillary tube. So immediately if you operate your compressor at 1000 RPM, at this evaporator temperature, your compressor can only provide you this, whereas your capillary will continue to provide this. So you will have evaporator flooding. You will have evaporator flooding. The evaporator gets flooded, the pressure inside will rise. Okay, once the pressure inside rises, instead of operating here, you will be operating here. At this condition, you will have this much flow rate provided by your capillary tube. Okay, and this will continue to go on till you reach a new balanced condition, which is this. So this will be your new evaporator temperature. So your capillary tube will move along this line and your compressor will move along that 1000 RPM line. What was given initially was the 3000 RPM compressor. Last problem is, I think you should be able to do it because I have discussed one similar problem in class now.